Hi to everybody, and thanks to the organizers. I want to take this chance to talk about the equal time spin kinetic theory and as an example, the spin transport as well as the CKT. And then I will introduce our recent work about the collision terms in the spin transport and show how to derive the equilibrium distribution function from the requirements of detailed balance. So these two topics are based on, next page, okay. So these two topics are based on our work last year and a recent paper. So first, when describing a classical system, one just needs to obtain the classical particle number distribution function. And the kinetic equation of the distribution function is just a Boltzmann transport equation. And for a classical system or the particles, the quasi-particle approximation always applies and all the particles are on the mass shell. But when it comes to quantum systems, things are quite different because first the quantum system involves more intrinsic degrees of freedom, such as the spin. And ever since the discovery of the spin, it is involved in many interesting new phenomena. And in order to describe the transport phenomenon related to spin, it is also required to calculate the spin distribution function. And also in the quantum system, the particles are generally off the mass shell because of the interaction with the medium and also the off-shell scattering process. So the quantum analog of the classical distribution function is the Wigner function. The distribution function is, as we all know, is defined in the phase space, which has a coordinate and a momentum at the same time. However, we know that in the quantum mechanics, you cannot specify the coordinate and momentum at the same time. And so when going from the classical distribution function to the Wigner operator, you first set from the density operator, which involves a field operator that has different coordinate. And the Fourier transformation is performed with respect to the relative coordinate. So you can have the center of mass coordinate and the momentum at the same time. And if the system is placed in the external background field, there is also a gauge link to guarantee the gauge invariance of the Wigner operator. And then the Wigner function is the ensemble average of the Wigner operator. So in order to derive the transport equation, you first need to have the kinetic equation of the Wigner function, which follows from the equation of motion of the field operator, which is either the, for a quantum mechanical system, the Dirac equation, Klein-Golden equation, or a system with interaction, that is the Dyson-Schwinger equation. For a QED system or QCD system, this kinetic equation for Wigner function has been derived in very early works. However, the covariant kinetic equation for the covariant Wigner function is related to the fields at all times, and the Wigner and the Fourier transformation is performed also to the time parameter, so it cannot be solved as an initial value problem. To solve this problem, the equal time Wigner function is defined, which is very, very similar to the covariant Wigner function, but the difference lies in that the field operator here have the same time parameter, and the Fourier transformation is performed only to the spatial coordinate, but not the time. And in an external electromagnetic field, the kinetic equation of the equal time Wigner function is just the Dirac-Heisenberg-Wigner equation, the DHW equation, which can be solved as an initial value problem and has been applied to problems such as the Schwinger pair production, where you need to solve it as an initial value problem. But however, later it was discovered that the equal time Wigner function and its kinetic theory is not actually equivalent to the covariant one, because the covariant Wigner function involves a Fourier transformation of the time parameter, and thus it is equivalent to a collection of all the energy moment of the equal time Wigner function. Oh no, what happened? Okay, so sorry for that, and let's continue. So only when the particles are on the mass shell, then the zeroth order moment of the equal time Wigner function is equal to the covariant one and is enough to describe the system. So then there are 4 steps to construct a quantum kinetic theory for spin 1/2 system. The first step is to derive the covariant kinetic equation for the Wigner function, and it follows from the equation of motion of the field operator, either the Dirac equation, the Dyson-Schwinger equation, and so on. The presented ones are for a fermion system with chiral condensate, but with mean field approximation. And then from the covariant kinetic equation, one constructs the equal time hierarchies for the infinite moment of the equal time Wigner function. But the lucky thing is actually only the lowest 3 moments are involved generally for a collisionless system. And for spin 0 particles, the lowest 3 moments of the equal time Wigner function would form a closed subgroup. And for fermions, the spin 1/2 particles, only the lowest 2 moments of the equal time would be enough. And then the last step would be to perform the spin decomposition, as the Wigner function itself is not a physical quantity, but the spin components have definite physical meanings. For instance, the F0 and G1 are number density and current, and F1, G0 are helicity density, spin density, and so on. And also perform the spin decomposition to the kinetic equations, one would obtain the 16 constraint equations and 16 transport equations. So for a spin 1/2 system, the zeroth moment of the equal time equations would give the transport equations, and the first moment gives the constraint equations. If the system is massless, only a subgroup of all the equations would describe the phenomenon of the system. But when the fermions are massive, or the equations are coupled together, and which is the case we're going to derive in the following. And then in order to separate the classical transfer phenomenon with the quantum phenomenon, it is necessary to perform the semi-classical expansion with respect to the equal time component and also the 16 constraint equation and 16 transport equations. So the constraint equations would reduce the independent degrees of freedom. For massless system, there is only one independent component, that is the number density, and for massive system, there are more, actually 4, 1 for the number density and 3 for the spin density. At the classical level and also the first order of H bar, all the other component can be expressed in terms of the number density and the spin density. And at the first order of H bar in the constraint equations, there are also contributions from the interaction of the electromagnetic field with the spin, which are off-shell effects. And then with those constraints, one can derive the equal time transport equation of the number density and spin density at the classical level and also the first order of H bar. Since we're considering now a system without self-interaction, but only the interaction with the background electromagnetic field. We have at classical level the free streaming transport equation of the number density F0. And at classical level, there is already effective collision terms, which stands for the interaction of the electromagnetic field with the spin. And at the first order of H bar, the transport equation of the number density and spin density are coupled together, and they are all involved with the spin interaction with the electromagnetic field. And those four equations are valid no matter how large the quark mass is, as long as the quark mass is a constant, not from the chiral condensate that is depend on the space-time. And these four equations can be solved order by order as the initial value problem. And now, since the system is massive, all the components are coupled together, yet we can still introduce the same chiral component as the massless system and compare between the both. Now, although we have introduced the same chiral component, it is related to some other component of the Wigner function. And when the mass is extremely small, we can take the Taylor expansion with respect to the mass and keep to only the first order of mass. And we find we can derive the same free streaming part as a CKT equation. And the terms with respect to mass can be seen as the effective collision terms. And if there is electric field in the system, the mass effects start to appear at classical level. And if there is only magnetic field, the mass start to appear at the first order of H bar. And it is also involved the inhomogeneous, the mass correction is also involved in homogeneous of the system. And so when considered the CME case where the system has only magnetic field, we can ignore the electric field of the system. And we find that the mass correction to the CKT equation only appears at the quantum level, and which means the mass correction to the chirokinetic theory is very small, and also it is related to the inhomogeneous of the system. And this equation, the mass correction to the CKT, can be solved perturbatively, namely one first solve the effective collision part, and then the four CKT equations. So next, I'm going to the second part of my this talk. I'm going to talk about the collisions in the spin transport series, and also show that the equilibrium distribution function can be derived from the detailed balance requirement of the collision term at equilibrium. So first, why do we need the collision term? Since recent years in theoretical studies and experiments, it has been found that a huge orbital angular momentum is produced in the non-central heavy ion collision, and a part of this huge OMA is transferred to the spin polarization of the particles. And as a result, in the final state, the emitted particles can be the spin of the emitted particles can be aligned with the orbital angular momentum. And the global polarization measures the vorticity and the spin polarization in the as a whole in the system. And it is found that the global polarization is a robust phenomenon, which means that the different theoretical approaches have the same or almost the same result, and is in agreement with the experiment. However, when it comes to the local polarization, there is still the sign problem, and there are different proposals to solve the sign problem, such as maybe we understand the vorticity in the wrong way, or maybe there is the gluon carries some of the vorticity and alignment, and also there may be some off equilibrium effect. And so if we want to deal with this off equilibrium effect, the collision terms would be important in the evolution of the system. And in the past few years, the spin transport, the free streaming part of the spin transport has been well developed, but the collision terms are still under research. The collision effects related to the spin has been listed below. And these works try to answer the questions of, for instance, how does the global orbital angular momentum transfer to spin polarization? And does the spin degree of freedom reach local or global equilibrium? And how does they reach the equilibrium? And when does they reach the equilibrium? And they also try to describe the spin diffusion effect in the system. And also, the distribution function itself is a co-ingredient in the kinetic theory and also the equilibrium many-body physics. So its derivation is of huge significance, maybe. In fact, it has been derived with different approaches, and different forms of the equilibrium distribution functions has been obtained. For instance, it can be derived from the density matrix for the spin 1/2 particles, or by analyzing the free streaming part of the spin transport. But the most optimal situation would be to derive the equilibrium spin distribution function from the collision term by the requirement of the detailed balance at the equilibrium, and also by maximum entropy. In fact, for massless fermion system, the equilibrium distribution function has been proved to satisfy the detailed balance in previous research. And in this work, we work in a massive system and show that the equilibrium spin distribution function can be derived from the detailed balance principle. So I will just briefly go through the framework of this work. It is generally based on Dylan's work in February this year. And since Dylan is going to give a talk day after tomorrow, maybe he will give a detailed review. So I would just briefly go through the framework. The framework is just a general framework, including the a general spin transport theory, including the collision terms. When facing a quantum system with interaction, one naturally goes to the field theory. However, when you deal with a system in an off-equilibrium system, in order to still have the full power of the field theoretical techniques, there are different ways. One of the ways is to have the complex time path surrounding the real-time axis, also known as a Keldysh contour, and replace different ordering of operators by placing them on different contours. And then the Green's function and the self-energy become metrics, and they still satisfy the Dyson-Schwinger equation, which is now the equation of motion on the complex contour. From the Dyson-Schwinger equation on the contour and perform the Wigner transformation, one would obtain the Kadanoff band equation. And then we take the approximation that we work in the chiral restored phase, so that we the fermion only have the current mass, and the mass does not have the space-time dependence. And we also have the quasi-particle approximation. with these two approximations, we can obtain the constraint and transport equation by summing and subtracting the both cut-off band equations. And then the next step is to take the spin decomposition of the Wigner function, the self-energy, and also the collision terms, and we will obtain the component equations. The right hand side of these component equations are the collisions. So there are actually 5 components of the Wigner function, and 2 of which are the vector charge current and axial charge current. They have physical meanings, and all other components can be expressed in terms of the vector charge current and axial charge current. So we take the V and A as basis and derive the transport equation of the vector and axial charge. With the on-shell condition and the restrictions of this two, because actually V and A has in total 8 components, but with the restrictions, there were only 4 degrees of freedom of the system, still 1 for the number density and 3 for the spin density. And with these restrictions and on-shell conditions, we can derive the transport equation of the vector charge and axial charge current. So the first is the zeroth order transport, the classical ones. The left-hand side is the free streaming part, with the right-hand side are the collision terms, and also the first order transport. These equations looks very complicated, but well, the terms in the gray boxes are local collision terms, which describe the dynamical effects such as the diffusion effect or maybe the spin exchange process. And the terms in the orange boxes are involved with the non-local effect, because they have they comes from the gradient expansion and has spatial derivatives, and there are quantum effects and are related to the correlated transport of the vector charge and the axial vector charge. And with those terms, the polarization can be generated in an initially unpolarized system. But however, in those equations, the self-energy has not been specified, because we have not specified the interaction of the system. And in order to derive the equilibrium distribution function, we need specific self-energy expressions. And in the following, we were going to specify the interaction and calculate the off-diagonal self-energies and also the equilibrium distribution function. So since we focus on...
Sorry, 5 minutes remains.
Okay.
5 minutes remained.
All right.
Okay, it's just information.
Okay. So since different interaction determines only how fast the system reaches equilibrium state, but not the equilibrium distribution function itself, we will take only the very simple NJL type model with scalar channel of interaction. And we take the approximation that we work in the chiral restored phase, and also takes the 1/NC expansion and also the semi-classical expansion. And in the 1/NC expansion, there are different components of the self-energy, and we take only the very simple one with the trace, because it has simple Dirac structure, and in the principle of detail balance, the gain term and the loss term cancel with each other in arbitrary collision channel, so it does not lose any generality to take only one component of the self-energy. And then with the explicit expression of the self-energy, we can substitute it in the zeroth order transport equation, and by the requirement of the conservation of the energy momentum, there are only quark-quark scattering process and quark-anti-quark scattering process. In the following, we're just going to consider the quark-quark scattering process. The detailed balance requires that the collision term vanishes for both the transport equation of the number density and also the vector charge and the axial vector charge. We then can derive the equilibrium distribution from the detailed balance at the classical level, where the number density distribution function is just the Fermi-Dirac distribution function. The derivation comes just from the textbook calculation. And for the axial charge distribution function, we now have find only a trivial solution that at classical level, there's no axial charge distribution function. It exactly equals to 0. There may be non-trivial ones, but maybe it depends on interaction. And but the trivial solution of the axial charge distribution function agree with the power counting that is used in other researchers with the collision terms. Since in the power counting, the spin polarization is generated from the coupling between spin and the electromagnetic field or the vorticity and their quantum effect. So at classical level, there is no spin polarization, and the spin polarization only generates as a quantum effect at the first order of H bar and higher levels. So the first order transport equation is required, but with vanishing classical axial charge current, the first order transport equation is greatly simplified, and the term in the orange box would generate spin polarization from the thermal vorticity and even in the initially non-polarized system. Substituting the self-energy and also the zeroth order solution of the equilibrium distribution function, that is the Fermi-Dirac equation, for the vector charge distribution function and zero axial vector charge distribution function at classical level. And by the requirement of the detailed balance, we will have non-vanishing spin polarization at the first order of H bar, which is in agreement with previous researches. And since the collision terms involves the spatial derivative, which comes from the gradient expansion, maybe it is also a non-local effect, and maybe it is related to the orbital angular momentum. We will check it in our future work. And so, thank you. I have talked about our work about the equal time spin transport and how to derive the equilibrium distribution function from the detailed balance. And thank you for your attention.
Zhu, thank you for a very interesting talk. So please, questions. Are there questions?
Yes, I have a question.
Okay.
Yes, can you go back to the last slide?
This one?
Last slide, your last one. Yeah, this is a detailed balance vanishing the collision term. So yeah. What's, so I mean the first order, a mu.
Yeah.
Right. Is this some kind of vorticity?
Yes, it is some kind of vorticity because in the right-hand side, can you see my mouse? No, I can see my mouse. Because there are the derivative on the on beta. Beta is U over temperature. It is
yes.
some vorticity. Yes.
So what about the zeroth order A mu? So what's
zeroth order, we have shown that it equals to 0. We haven't find non-trivial solution at classical level. Maybe there is, but maybe it depends on interaction, I think. In the interaction we have adopted, there is no classical A mu.
Did you solve this equation at the first line?
Yes, I have solved it. Yes.
So you found the solution in this.
Yes.
So why do you think it's a detailed balance? Balance of what?
Detailed balance requires that the collision term vanish, and I solved the equation in the first line by requiring that the collision term vanish, and it will give the solution to the equilibrium A mu, the first order equilibrium A mu.
Okay.
Okay. Arpan, I don't.
Yeah. So in your calculation that you have considered the collision term, which is like a 4 Fermi interaction where all the fermions are at a fixed x, right?
Yes, they're at fixed x.
Yeah. So in this case, from where the non-locality might arise, because this is a local interaction, right? Because all the fermions are interacting at a fixed point.
It comes from the H bar expansion, and the H bar expansion also takes in the gradient expansion. There are derivative on the x. In this sense, it's I mean it's non-local in the derivative sense.
Okay.
Shulin.
Hi, Ziyue. Thanks for the nice talk. I have a question on since you used the 4 Fermi interaction. So your expression for self-energy, does it contain any divergence?
No. Since we did not perform the momentum interaction, because when you take the detailed balance, you require that the collision term vanish. The terms inside the momentum integration vanish. So we did not perform the integration.
But if you do, they will probably diverge, right?
Yeah, if we do the momentum integration, it will probably diverge. Yeah.
But it doesn't show up in your solutions since you require detailed balance. Is that right?
Yeah. Yes, that's
okay.
right.
Okay, thanks.
You're welcome.
Somebody
Sorry, can I comment on, make some comments?
Yeah.
So Shudin, I think basically this is what you consider is just this contact interaction, and it's just at the tree level. So basically you do not actually have this momentum integration at all. In your case, or in my case, when we consider, for example, QED, then certainly then you have to somehow integrate over these momentums of the exchange photons. So that lead to some divergence issue, and we have to deal with it more carefully, and it becomes more complicated. But yeah, in general, it's not a problem. If you consider contact interaction and tree level, then there will be no divergence at all, I think. Yeah.
Sure, I see. Okay, thanks.
I don't see any other questions. I have questions to the first part of your talk. There you work with the equal time formalism.
Yeah.
But if you work with on-shell particles, it seems to me it is automatically equal time formalism, but you cannot do it equal time, but in this way to proceed with the covariance of all the equations. Because look, if these are only on-shell particles.
Yes, if there is only on-shell particles, the P0 equals to the energy, and it is equal to the covariant one.
Yeah,
Yes,
that's they stick to the mass shell. So
yeah.
then, okay, then, but it is much more convenient to have covariant equations. Then it seems to me.
Yeah. It's true. If it is always on shell, it is more convenient to work in the covariant one. But if you want to have if you want to include the off-shell effects, then the constraint equations will give different different result from the covariant ones.
Then many spectral functions are invented, just more model spectral functions which just model these off-shell effects. So that it seems to me this is another way to do it. It's not necessary to microscopically calculate the spectral function. It's possible just to postulate the spectral function and just calculate parameters of the spectral function, and still you will have covariant equations. So, which is important to my mind. Just another possibility. So that's question or comment, up to you.
I'll take that as a comment.
Okay.
And I will think about that.
Thank you very much once again.
Thank you.